Great.
Are you ready? Okay, so our next speaker in the session is Clément, who is going to be telling us about a new extension of the ML.
Thank you. So hi, everyone. My name is Clément Blaudeau. I'm going to present the result of my PhD thesis, basically, that I've defended last month. Okay, so let's start with a bit of context on ML modules. It allows me to? Yeah, okay. So let's start with a bit of context. What I mean by modularity is, I would say, the hard form of being able to identify natural boundaries inside programs and gather components that make sense together inside what we call modules, and to identify also components that can be reused throughout the system. The tools for achieving this are basically the ability to define, control, and enforce interfaces, the ability to abstract part of the code and consider things as black boxes, ways to control namespaces, and finally, ways to combine the different modules that you've built through what we call composition. In programming languages, that takes a lot of different forms, functions, interface files, libraries, but there are, I would say, three main approaches that provide the whole set of tools for modularity, which are the object-oriented programming, type classes, and the module system, the one I'm going to focus on today. So let's do a super quick introduction on ML modularity. Let's define a library that handles complex numbers as a pair of floating point number. So we can gather all the definitions of our library inside a structure that is defined with those keywords, struct and end. And we can put inside this structure as many type definition and value definition as we want. Then we can access the content of a structure through this dot notation outside of the module. We can then define interfaces that are called signature in the ML nomenclature. And here we can define the interface of a mathematical ring where the type definition is left abstract. And we can use this interface that we've defined to restrict the outside view of the module. And if we do so, then the rest of the program doesn't know that complex are implemented as a pair of floating point number, and the type checker would refuse to consider this invalid polar representation as a floating point number. We can also use interfaces to enforce polymorphism, and we do so by defining what we call functors, which are not the category theory thing. And a functor is a module that takes as input another module. Here it's polynomial implementation over any ring. And as you would expect, we can call the functor on the complex module. But we can also realize that the polynomials themselves form a ring, and we can get the sets of polynomials with two parameters by just calling the functor again. So the main takeaways is that we have a separate language layer. The module layer is a separate language built on top of normal core level OCaml, or ML in general. And basically, modules are a small calculus with records and function and explicit type ascription. And the things that makes them a bit tricky sometimes is the fact that you have types within terms, basically. So you have those type definitions, and they can be abstract, and they are within the terms. And you have this telescope mechanism where once you've defined a field within a record, it's accessible through the rest of the record. So it's not dependent records per se, but it's a form of telescopes. And also note that the way we separate the different fields is only with spaces. There are no like semicolon or anything. Okay, so what's up with OCaml modules then? So the OCaml modules are quite renowned for having rich abstraction mechanisms and being quite extensively used in practice. And also there are new features that are being actively developed and that I think are quite exciting. But the problem is that the specification of what's going on in OCaml kind of dates back to the late 90s, so it's a bit out of date. And when you have an out-of-date specification, it means that at some point you have unsupported edge cases that start to pop up. The system becomes harder and harder to predict, and also harder to use in some advanced cases. And so the goal of this work, and basically of my thesis, was to try to build a specification for OCaml modules that would not have any of those issues, but could also be used to retrofit the existing type checker. Not just replace it with a new thing that would be perfect, but retrofit the existing. So what I mean by it's a problem to have a not dated specification. Let's look at a couple of examples. There is a property that I like to define as robustness, the idea that there are some changes that are semantically equivalent, and they should not break the type checking. And it's not the case in current OCaml at the module level. Let's look at this example. It doesn't matter, but the thing is that I'm going to do a beta reduction and inline the definition of the module X, and then the type checker will refuse this expression. Sadly, type checking is also not stable under beta expansion, where you have some code, not very important, but it type checks, and you add an intermediary definition, and it breaks the type checking. The two problems come from very different aspects. The first one is what we call signature avoidance. The second one is the problem of module identities. And in this presentation, I'm only going to focus on the first one. So let's talk a bit about the infamous signature avoidance problem, at least infamous in the ML module community. So it comes from the interaction of three things. First, we have those abstract type fields that I've shown before, very important to enforce invariance. Then we have these dependencies within the fields of a signature because of this telescope that we've seen. And we have also operations that are going to remove fields of a signature, and they will create dangling dependencies, basically. So let's look at an example that is basically an instance of the previous one. We have two modules, N and M, and I'm going to inline the definition of N. N contains a type definition, T, and then a submodule that mentions this type definition. And if I do inline the definition of N inside of the definition of M, then there is a reference to this type T that has gone out of scope. And the type checker doesn't know how to resolve this reference, so it fails. So this is a problem, but it's OK because we have a failure. What's more worrying is that we also have silent errors, so what we call over-abstraction, kind of a similar setup where we're going to inline the definition of the module N. But here we have just type definitions, and the type U and V are equal, both equal to the type T. And if we inline the definition, then the type checker accepts the new definition, but it has abstracted away the definition of U and V, so they are no longer equal. And so the goal of the goal was to say, okay, we don't want over abstraction, and if possible, we also don't want to have any type checking fail when we have fields that go out of scope. So that's the problem that ZipML is trying to solve. And let's see how it works. So let's go back to the first example where we have a type definition, and again, OCaml would fail on that example. So let's take the signature that we have before we do the projection on the submodule X. And basically, it's a tree-like structure where we have dependencies between some of the part of the trees, and especially the value X mentions the type T. So of course, if we just project by removing the fields that are no longer visible, we create this dangling dependency. But there is a classical technique in functional programming if you want to focus on some part of a tree-like structure without losing the rest of the structure. And this technique is called the zipper. And the idea is that you would not throw away the part of the structure that you're not interested in. You would keep it on the side. You would basically invert the arrows. And so you keep all the type information that you need in order for the resulting signature to remain valid. So what ZipML would output in this context would be that the module M only contains a value X, but also has an attached zipper where the type definition is preserved. And that's basically that's all there is. We extend the signature language with this notion of zippers, where the zippers, they act as a hidden typing environment that is attached to the signature. But if we do so, then if we only do that, then every operation that might create dangling dependencies will create new zippers that might pollute the resulting signature. So we also have an operation that we call zipper simplification. So I'll just make the example a tiny bit more complicated, where we have two type definitions. And we have a module X where we have a type definition and then a value definition. So again, OCaml would fail on an example like this because X would be hill-typed. So in ZipML, what we would do is we gather all the components that have gone out of scope with the projection, and we put them in a zipper. And then we might realize that, okay, so type T is abstract, but type U is just an alias of another type definition, so we might as well inline it, right? And if we do inline it, then we see that U is not used anymore in the visible part of the signature, so we might as well get rid of it and garbage collect, basically. So that's the first part of simplification. And then we might go a step further and say that we have T and V, they are both equal. There is one that is the definition point and one that is a copy of it, but we could invert those type definitions. And we get something that is equivalent, where it's V that is abstract and it's T that is equal to V. And if we do this transformation, then again, we realize that the type T no longer appears in the resulting signature, so we might as well get rid of it. And we end up with this signature that is equivalent to the first one, but is also valid in the source syntax. So basically, OCaml could have found this signature. And so that's I think that's the power of ZipML. Is we use zipper to prevent avoidance, and then we use simplification to go back in the source syntax if we can. So just a glimpse of what it looks like to what ZipML looks like on the inside. So we have a projection rule where we can take any module expression X module expression M, sorry, that contains a submodule X, and we can project onto it. We just gather all the fields, the declarations that the module might depend on, and we put them in a zipper. And this is typically a rule that is very problematic in systems that don't have zippers. We have a zipper removal through subtyping. So if you have a module that has a zipper signature and you do an ascription to force a normal signature, then the zipper disappears. And this is in the normal workflow of an OCaml developer. This is typically what happens when the result of the inference of the ML file meets the MLI file. So the idea is that ZipML is not implemented yet, but if it were, probably most of the time the developer would never see the zippers. And finally, we have this floating garbage collection of useless fields with a mechanism of simplification. And we also have a theorem stating that the simplification that we do actually never prevents further typing. So we never have this over-abstraction where we might lose visible type equalities. The main properties of ZipML, of course, is the soundness, and it's obtained by linking ZipML with previous works, and especially M-omega, which you can find in the OPSA 2024 paper. That is basically the latest iteration in a very different line of work, where ML modules are understood via elaboration in F-omega. And so there is a soundness theorem that is what you would expect. And it's obtained by elaboration of ZipML in M-omega. And there is a conjecture, and conjecture is not because we're not sure it's true, it's because in France, PhDs are 3 years, and so I didn't have time to finish the proof, but I think it's true. So we have a conjecture that M-omega, so maybe the standard approach to typing module systems, and ZipML, that is more of a custom approach to typing module system, actually have the same expressivity, meaning that the zippers that we use the zippers that we have can be used to represent quantified variables and the mechanism of extrusion that you have in the Effing line of works, basically. So you have this kind of big picture of OCaml on one side and F-omega on the other end, and we have links that are quite strong between the intermediary points. Okay, so let's sum up. So I've presented quite quickly ZipML, a robust type system for OCaml module that doesn't have the beta extrusion and so the two issues I've shown before. It uses internally syntactic signatures. By syntactic, I mean source signatures just extended with this small notion of a zipper, which is the same as the current OCaml typechecker does, basically. And it solves the signature avoidance problem with the introduction of zipper signatures. There's more to ZipML in the paper. There's actually quite other aspects that I have not developed in this presentation. The first one being the mechanism of module identities that solves the second problem that I've shown. That is approached with the notion of transparent signatures. In ML module systems where you don't elaborate into F omega. You have the problem of strengthening that is also quite infamous. And it is solved in ZipML I think, in an interesting way with laziness built in. So the type checker would not do unnecessary work. And finally, we have a mechanism that is often overlooked, is the preservation of user-written definitions. So as I've shown in the first example, the user can write some type definitions, intermediary type definitions. And in most formalization of ML modules, those are just inlined away. But for practical purposes, they are very important, especially because the type expressions can be very big. So yeah, ZipML has a mechanism of normalization and keeps all those user-written type definitions. And the most obvious future works are to get it into OCaml, and also to maybe do some user surveys, understand what are the practical heuristics we need for the rewrites. Sometimes you can remove a zipper by inlining all the type definitions that they are in, but this would explode the size of the signature. So sometimes maybe you don't want to inline the result. And those are the kind of practical heuristics that we need to explore. And I finished by saying that you should watch the research space of ML modules. There are new things that are coming, and I think they're pretty exciting. Thank you for your attention.
Okay, we have time for questions. I have a question. Is there an interaction between your extension and error messages? Right. Have you thought about whether it makes them better or worse?
That's a very, very good question. So the other approach that I've mentioned, the M omega approach, technically has the same expressivity as ZipML. So you could use it as a replacement of the type checker. But one of the things that we were worried about is the fact that it would probably produce very obscure error messages. Whereas with ZipML, if you have a situation where you need to simplify the zipper away and you cannot, you would have precise program points that you have user-written names, and you could produce an error message that would be understandable by the user. At least I believe so, because I have not implemented it yet, but it seems well suited to have good error messages.
Okay. We have some more questions in the back.
Hello? Me?
Yes.
Yeah. Hi.
Yeah.
Maybe OCaml has formatted my brain too much at this point, but I can see the case where simplified away, but that like this mic. But yeah, when there needs to be a type left in the zipper, like that type definition should be there in some way, and so wouldn't it be better to rewrite your module?
So the key idea of using zipper is that you can delay the point where you actually throw the error, and if you have to print the result of the inference to the user because it tries to extract the MLI file or is doing module type of this kind of things, then if you were not able to simplify, you would have to throw an error, but you wait as long as you can, because sometimes other operations on the module makes the fields that you've kept in the zipper useless.
So it's not something you would keep in your ML or MLI file?
No, it would not. The idea is that it would not appear in the MLI. The user is not able to write zipper signatures. It's just the internal representation is made flexible. And so the type checker doesn't have these weird syntactic rules that it currently has to prevent types from escaping scopes.
Got it. Cool. Thanks.
Thank you.
Okay. We need to get the next speaker up. Right here in the back, we have time for one quick question while we switch.
I'm not too familiar with the CAML modules, but does your mechanism might be preventing some legitimate intentional uses, like some hiding of the types or not, which users might have done because they wanted to do it, and your scheme will eliminate them because they think it's errors?
So that's a very good question. The way it works is that if the user wants to lose type definitions, he can, and the user can abstract type definitions, and it can hide internal details of the module. But what's going on right now in OCaml is that sometimes those definitions are hidden away implicitly, sometimes it doesn't work. And with ZipML, you have a clear specification of when does the actual disappearing of fields actually occurs.
So it might break some existing code, maybe not really.
No, I think it would be fully backwards compatible, except if people used. No, it would be fully backwards compatible. You cannot use the fact that you would know the two types are different. You can only use equality.
Okay,